Good afternoon, sir.
Good afternoon. Yes, I'm in time,
Yeah, sure.
very much in time. So, how do I start? I put my PPT where?
You can go for share
Share. Where is the share command?
in the bottom.
Share. Okay, yes, here is share.
Okay.
And
You have opened, sir. Open your PPT already.
not yet, not yet.
You have to open first. You have to open your PPT on the laptop.
Okay, now I'm on desktop, but I will open the PPT. I'll have to minimize this.
Yeah, no problem. Yes. You have minimized on the laptop desktop. Okay.
And
So you first share it. Share it from the bottom.
now I open the PPT and I minimize it.
Share, sir. Share it.
Okay, I'll come to that. Where am I now? This is my PPT, but where am I in the? Here. Okay.
Share content is there. Share.
Share. Yes. Share.
Click it, sir. Click it
Huh?
here. Click it. Click it.
Click. I clicked.
Click it. Just click it here. Share.
Screen.
This icon here, na? Share icon.
Share content. What do you want to
Yeah.
share?
Yeah.
What do you want to share?
And share, that is PPT. Click the PPT now.
This
If you
one.
want to show,
Oh
if
yes.
you,
Click the PPT.
yeah,
Okay. Is it visible to you?
not yet.
Not yet. Share the PPT. How do I share? I open the PPT,
Yeah, open the PPT.
but it goes to another screen.
You, sir, keep it down on the lower menu bar. And after sharing, you can open it.
Okay.
Sir, I think it would be helpful if he shares the whole screen.
Share. Attach a copy. PowerPoint presentation. Attach a copy. Is that?
Sir, have you just share the content? Share. Share icon is there in the lower part.
Optimize for text, image, screen.
Yeah,
Share.
screen. Yeah, screen.
Screen. Shall I click on the screen?
Yeah.
No. Share. Entire screen window Chrome. Cancel. Connecting. Sharing. Says connecting.
Yeah.
It should not take this much time.
Is it still connecting?
Okay, it says connecting and something is rotating. Share content.
It's not going.
Choose what to share. Entire screen, window, Chrome tab.
PPT is there, sir, somewhere PPT.
PPT is there on my desktop.
Yeah, the screen is going on. So you click the PPT there because PPT presentation is yours. PPT presentation. Na?
Here. It opens it on the desktop now. It opens on the desktop. But how do I share it?
You just click, sir, your PPT, whatever you want to present.
Yes. Shall I open it or not open it?
Yeah, you have to open it, sir.
And then share content, it still says connecting. I cancel that. Stop.
Again, sir, you need to connect.
Share. Share content. No. Something is not correct. Stop video. Share.
Sir, have you opened in? Yeah, it's okay.
Where? I don't see the PPT yet. It says stop sharing.
Yeah, stop sharing, stop sharing.
Stop sharing.
And then come to sir PPT. There was some window of PPT.
Sir, the way he has, sir, Anil sir, the way you have shared, you just do the same thing and then you can open the PPT for because whole screen was shared. So you can just open the PPT and as you're working on the screen, you can do it like that itself.
So I first click on share.
Yeah.
Share.
And
And
share
then
the whole screen. Share the whole screen. You can do.
Yes, Mr. Ankur, you can just help him to connect.
So in share contents, you may find that there is option of share screen.
share screen. Screen, yes, screen.
Yeah, click on that.
Okay, clicked. Now share content connecting. Should not take that long.
Is there any okay option or anything is there? Okay,
No, connecting, share connect content, share. There is another window. Choose what to share.
yeah. So there you might have got share screen and then you have got share content, some PPT and all those things are there maybe.
So, is it now visible to you?
Not
No.
yet, sir.
Eh? Not yet.
Not yet, sir. Just few
Share.
minutes ago it was visible.
Sir, or else send
Before
the PPT to host so that sir can share.
I should have sent it.
Send the
I should have,
PPT to host, sir, through email.
eh? Share. OneDrive, Windows 5, OneDrive, sign in. Copy set. That's a copy. I get email window to send you. Shall I send it to you? But it won't go. It's very huge. 9 MB. No, it's not working. This is not working. What do I do?
सर सर फर्स्ट ऑफ ऑल सर
Yes.
पीपीटी ओपन कर लीजिए विंडोज पे
Eh?
पीपीटी ओपन कर लीजिए सर पहले
मैंने खोल
पीपीटी
दिया था पीपीटी है ये यह है सो ओपन
ओपन है
करूं
सर पीपीटी हाँ ओपन
है
है सर हाँ सर आप शेयर बटन पे क्लिक किए सर
शेयर बटन
क्लिक कर लीजिए सर
शेयर बटन तो मैं क्लिक कर चुका हूँ वो तो
हाँ
घूम
सर
रहा है
इज नॉट कनेक्टेड सर उसके बाद सर वो पीपीटी पे क्लिक कर दीजिए पीपीटी आएगा विंडोज आएगा एंटायर स्क्रीन आएगा
जी मैंने पीपीटी पे क्लिक कर दिया वो तो मेरी विंडो मेरी स्क्रीन पे दिखा रहा है खाली
स्क्रीन पे नहीं आ रहा।
खाली मेरी स्क्रीन पे दिखा रहा है मीटिंग इन प्रोग्रेस बिल्कुल
तो सर एक बार जो सिस्को में आके सर शेयर ऑप्शन होगा शेयर तो किया
शेयर ऑप्शन है मैंने शेयर ऑप्शन किया था
सर फिर से क्लिक करिए एक बार फिर से
इससे शेयर कंटेंट एंड इट इज कनेक्टिंग एंड गोइंग अराउंड फॉर हाफ एन आवर
हाँ सर घूम रहा है ओके
इट्स नॉट कनेक्टिंग इट इज नॉट कनेक्टिंग
सर एक बार लीव करके फिर से कनेक्ट कीजिए सर लीव करके फिर से एंटर कीजिए
कैंसिल
मीटिंग में
क्या है शेयर क्या है
सर जी
शेयर doesn't share I can see your screen my screen you can see me
sir can you send me the ppt to on my email
email you it won't go it's huge I have to put it on my I have to put it
okay
on my what is it called drive
okay
I should have done that before entire screen how do I put it on the drive I forgot
sir you can leave first and then again you can enter I think
what do I do
sir first you leave it from the meeting and then again enter it
so I log out
yeah leave
okay
the meeting from bottom side it is the end meeting
and meeting
leave meeting and then again you enter it
The
it won't
red cross is there, sir. Just beside the share, there is a
yes,
red cross.
yes red cross is there yes
Yeah. Yeah, just click on that and then again enter.
it's not clicking not allowing me to leave
It
I
has
should
hanged.
I should cancel share and then I can leave the meeting. Leave meeting, yes. It's not allowing me to leave also.
ये घूम रहा है
Then what you can do is, sir, you can click the cross button of the window.
Yes.
You can click the cross button of the window. So that might help.
Okay.
yeah
Leave site, yes. Leave. Start video. And unmuted. You can hear me now. Now I
Yes, sir.
now I go to share.
Now, yeah, you go to share button,
Yes.
and now you will find that share screen. The
Yes.
entire screen is, yeah, click on that.
Click on that. Yes.
Now what is happening?
Yes,
Is
sir.
there is an OK or share? Is any other button is there after clicking on share? It's share entire screen.
It's connecting, and I can see myself in a small window and that screen, and
Okay.
my PPT is not there.
Okay, fine. It once it gets shared, actually we also cannot see it yet. So once it gets shared, then we can go and navigate through it.
So what do I do?
You can see your screen in the window.
No.
Sir, you can do entire screen. Click the entire screen.
Entire screen.
Yeah.
Where is the
There
entire
is-
screen?
No, in share itself there is an option of entire screen.
Now it's not allowing me to click that unless I stop the sharing.
Yeah, you can stop sharing.
Okay. It's not allowing me to do that also. And even the cross button, it doesn't work. Moderated, unmute mode.
आपने sharing की बात आता है ना share करें. Sir, have you click share, na? Click share,
Yes, I click share.
and thereafter you have so many options there. Entire screen, window, PPT, whatever.
No, I don't. I have my name coming up, entire screen, window, Chrome.
The entire screen. Click the entire screen.
Click the entire screen.
Entire screen. Yeah.
No, it is it's not clicking.
Yes, sir, it is coming. Yes, sir.
Minimize the window, sir. Minimize the window.
Yes.
Yes, you can open the PPT now, sir.
Open the PPT, sir, first.
Open the PPT.
सर पीपीटी बस ओपन कर दीजिए पीपीटी अपनी विंडो शेयर्ड है आपकी यू कैन ओपन द पीपीटी नाउ yes it's okay sir
Okay.
okay fine
I can't see it.
we are seeing sir we have visual here
Okay. So I click. There's a window with blank, and then say stop sharing. I click on this.
No, sir. Don't stop share. Click on stop sharing.
Okay.
You can start presentation because it's basically I cannot see the WebEx window down here there. So what you can do is you can start presentation. All of us can see it, and we can see you as well, sir.
Okay, let me just go to next screen. You can see this?
Yeah. We can see everything, sir. You
okay,
can
I can't see myself, but doesn't matter. I can stop like this.
Yeah.
Okay, thank you.
You
Thank
can
you very
open
much.
the presentation mode also, sir, if you want. Means you can
Okay,
press
I can
F5
do that.
and then.
Yes, it's presentation mode now.
Yes, sir. We can see the presentation.
Okay.
You can see.
Yeah sir it's okay now I think
Yes.
just I am introducing Professor Anil Kumar.
Yes, please.
Professor Anil Kumar is an experimental physicist known for his work in the field of nuclear magnetic resonance spectroscopy He did his college studies at Merit College, Agra University, from where he graduated in 1959 and completed his master's degree in 1961. And then he has studied at IIT Kanpur, also graduating with a PhD degree in 1969. Thereafter, he moved to United States for his postdoctoral studies, 1 year at Georgia Institute of Technology, Atlanta, and 2 years at the University of North Carolina. He also worked with Nobel laureate Richard Ernst and Kurt Wittrich during 1979-80s at Zurich, Switzerland, where he participated in the pending work on 2D NMR spectroscopy. Thereafter, he joined the Department of Physics in 1977 at Indian Institute of Science, Bangalore. He then was senior scientific officer and assistant professor, and thereafter became professor in 1990. Professor Anil has major contribution in the field of NMR, quantum information processing, and NMR quantum computing. He, with his group, has successfully demonstrated experimentally distillation of pseudo-pure states, implementation of logical operations and gates in different atmosphere environment. Professor Anil is a fellow of Indian National Academy and the World Academy of Sciences, Italy. He is also a recipient of C.V. Raman Medal in 1993 and thereafter Platinum Jubilee Lecture Award of the Indian Science Congress Association, Professor Rangadhama Rao Memorial Award of INSA, IISc Award for Physical Sciences, and Alumni Award of IISc for Excellence in Research in Science. And he also D.I. Raja Ramana Prize Lecture in Physics of Jawaharlal Nehru Center for Advanced Scientific Research. He held visiting chair Conrad at France, and thereafter he has, after superannuation, he was designated as honorary professor at IISc Bangalore, and currently is National Academy of Sciences honorary scientist at IISc Bangalore. So this brief introduction about Professor Anil Kumar. He has done a lot of work in the area of NMR, and now he is working on NMR quantum information processing still. And sir, we welcome you in this FDP program on quantum computing. So please, sir, you can start your lecture.
Thank you very much. Thank you very much for the introduction. When you asked me to give a presentation in your institute in Gwalior, I readily agreed because my wife originates from Gwalior. So Gwalior is my sister.
Okay.
Although he knows nothing more there. So I'm very happy to share my knowledge with people in Gwalior.
Yes, sure.
Okay, today I'm talking about quantum computing and quantum information processing by NMR. Why and how? Let's begin. The NMR, the phenomena. The Hamiltonian is my mu dot B. The mu for the magnetic moment for nucleus is gamma h cross I, and then the B is the magnetic field. If you apply a steady B naught field along the Z direction, the interaction reduces to minus gamma h cross IZ B naught. And for I equal to half, IZ is plus minus half, and the degeneration splits into two. The gap is given by gamma h cross B naught, which is h cross omega naught. We call the Larmor frequency. The most commonly studied nucleus is the nucleus of hydrogen. Its resonance Larmor frequency in a magnetic field of 2.35 Tesla is 100 megahertz, or in Gauss 23.5 K Tesla. Gauss. Other spin-off nuclei are fluorine 19, which resonates at 94 megahertz at the same field, and carbon 13, which is naturally 1.1% abundant, but we can enrich it to get a better signal. However, we mostly work with natural abundant carbon 13, has a frequency of 25 megahertz. NMR was first detected by Bloch in Stanford and in Harvard in 1945, for which they shared the 1952 Physics Nobel Prize. NMR has major applications in structure of biomolecules in solution and MRI, and a minor application in quantum computing. I will give you a very brief introduction to the other two topics so that we see what are the various applications of NMR. The first one is the structure of molecules in solution. Uh, I give you only the one spectrum here. This is called a two-dimensional nuclear overall effect, in which it spreads the proton frequencies in two dimensions, and the cross peaks in this spectrum represent represent the distance between the proton at this axis point and at this point. And so it has a large amount of information about interproton distances in the protein. And if you feed this information to a distance geometry algorithm, it calculates the structure of the protein. And this experiment is used for calculating the structure of the protein. Each cross peak has information on the distance between two protons. This paper's notation. Professor Richard Ernst got the chemistry Nobel for developing one and two dimensional Fourier transform NMR. Unfortunately, he passed away very recently in June of this year. Professor Kurt Wüthrich got the chemistry Nobel in 2002. Actually, it was expected these two people would share the Nobel Prize, but they didn't share the Nobel Prize. And Ernst got it alone. Wüthrich shared it with two other people, but mainly he got the Nobel Prize for protein structure determination solution by NMR. And as you can see from this slide, that this paper has two Nobel Prize winners as co-authors. The second major application of NMR is MRI. In fact, it is so widely known that even a common man on the street knows MRI, and they say the NMR is MRI. Okay, so the MRI is came out of NMR. I just show you one very old first image that we had created using NMR of two tubes of water using two gradients, X and Y, Z. And you see this during X gradient one frequency and during Z gradient two frequencies showing two tubes of water. And this we published in 1975. And basically the same algorithm is used in all MRI techniques. The image quality after 1990 was known that it is going to be very, very useful. Before, when we did these experiments, we were skeptical whether it will be ever used, and we were so wrong. The Nobel Prize for Physiology and Medicine 2003 for discoveries connecting magnetic imaging were obtained by Paul Lauterbur, who did the first two-tube experiment, but not using 2D NMR, but using 1D NMR, and he was credited with the development, initiation of the MRI. Peter Mansfield gave spin echo techniques for getting the data for the whole plane in one go. And unfortunately, both these people passed away right away. MRI has revolutionized human radiology, and it is now hailed as a major contribution of 20th century science to humanity. Well, we come to the subject of this talk today, the third application of NMR, the quantum computing. You might have, every speaker might have repeated these things, but I have my own way of saying this. The all present day computers, we can call them classical computers. This computer that I'm using right now to talk to you is a classical computer. It uses binary logic, 0 and 1. And all computations follow from this, and you know answer. You see all these images that you see in the screen, they're nothing but zeros and ones. And It's very powerful, but it's very interesting. Feynman in 1982 suggested that it might be possible to simulate the evolution of a quantum system efficiently using a quantum simulator. He never talked about computing. He was only talking about simulation. Okay, and so, but his suggestion gave rise to a lot of activity in the field of quantum information processing and quantum computing. So what is now? What is so special about quantum systems? There are two important properties: coherent superposition and entanglement. A coherent superposition can be understood. A classical bit can exist either in 0 or 1, but a quantum bit can simultaneously exist in 0 and 1 with different amounts of coefficients. So you see, this has a lot of, it's almost infinite ways that you can create a coherent superposition. And so this gives you a very strong, very large resource for doing for processing information. It gives new possibilities. Entanglement, if you have states not resolved in tensor products of individual particle states, are used in quantum computation and teleportation. Of course, if to make use of these properties of the coherent superposition and entanglement, one has to write new quantum algorithms. One of the first quantum algorithms that was written in the year 1994 was Shor's algorithm. See, this prime factorization problem is a tough problem in mathematics. The thing is that the factorization problem increases exponentially as the number of size of the word, length of the number increases. And so it's an exponential problem. If you can convert it into logarithmic problem, then it's easily possible. That's what Shor did. And so instead of exponential scale up, logarithmic scale up, and so just to impress upon you as to what the advantage is, that if you have a 400-digit number, it'll take the age of the universe to find its prime factorization. In fact, that's the reason why our bank accounts are safe, because you can't find the factors. But Shor's algorithm and the military secrets are safe because you can't do this. You can't do prime factorization. So Shor's algorithm demonstrated that it is possible to do if you have, for example, this is just plugging numbers. That if you had a quantum computer with the same speed as the classical computer, then Shor's algorithm would factorize a 400-digit number in 3 years. As soon as this was shown, there was a great excitement in the field of quantum computing, and in fact, U.S. military funded a lot of work in this direction. But they were very frustrated. For 20 years that not much progress took place. Anyway, and today it is difficult to get money from them because you have to show progress in building a computer, which is happening now. There was for example, searching a unsorted database. You see, you take your telephone directory. It is arranged alphabetically, but not numerically. But if I give you a number and ask you to find the name of the person whom it belongs to, you basically have to go through the whole list. You can be lucky, the first number that you see is the one you're looking for, or the last number that you are looking for. So in general, it needs about n by 2 operations, which is a very large number. Grover, a graduate of IIT Delhi, while working in Bell Labs, he gave a quantum search algorithm, which takes only root n operations. And see, if this is a million, then a root n is only 1,000. So this is also very useful algorithm. They distinguish in constant and balance function. There are certain type of functions which are either constant or balanced. Constant functions are those which are independent of this parameter value. Balanced functions are those which have one value for half the parameters and another value for other half the parameters. Classically, it takes several steps to distinguish such functions. Joshua gave an algorithm in 1992 which does it in a single step. Then a quantum algorithm for linear system of equations. The State Lloyd gave in 2009 a algorithm which gave exponential speed up for solving linear equations, large linear equations. Okay, so these are some of the obvious applications. There are many experimental techniques which are being tried and with various degrees of success. Trapped ions was the champion in the beginning. Polarized photons were still used very much. Cavity quantum electrodynamics, quantum dots. There was a lot of hope that quantum dots will come up, and the hope continues. Cold atoms requires very special equipment, but if it works, it works. And then this NMR, which is more of a NMR is more of a demonstration, not a real computation. Okay, Josephson junction qubits, and this is now the most uh, technique which is being scaled up maximum, and this is where the quantum computer of today will come. Already there are several companies, including IBM, which have put out a large number of quantum computers on the cloud, and you can use them for. I'll show you in the end of my talk some of the applications here. A fully based ESR quantum computer. There's not much progress in this field. So now, quantum computing is using NMR. Why and how? All right, nuclear magnetic resonance will have small magnetic moment and behave as tiny quantum magnets. When placed in magnetic field, spin-half nuclei orient either along the field, we call zero state, or opposite to the field, is called state 1. A transverse radio frequency field, B1 tuned to the Lambda frequency spin, can cause transition from 0 to 1, a NOT gate, by a 100-degree pulse. And before quantum computing came up, we just called it a pi pulse. We never called it NOT gate. We were doing pi pulses right from the beginning of the NMR and not knowing that we were doing a NOT gate. Similarly, we apply a 90-degree pulse, it puts in coherent superposition, it's a Hadamard gate. And right from the beginning, we have been using 90-degree pulses in NMR to transfer magnetization from Z direction to XY plane and then detect it. But this is a Hadamard gate. So these are single qubit gates. Now, if to have multi-qubit gates, we need to have spins coupled to each other by some coupling. The moment I am talking about here is spin-spin coupling, and a control knot operation can be performed using J coupling, and I'll show you how. So nuclear spins are qubits. To do NMR quantum computing, you need a very homogeneous and powerful magnet. And these magnets actually were developed, and we have 8 of them in our center at IISc at one point of time. And this AV700 means 700 megahertz and 16.5 Tesla. But the most important point of that I want to emphasize is of these magnets is that they need a field frequency in stability in 1 part per billion. And this is what is needed for studying proteins. And so these magnets actually were developed for protein structure determination. And we use them, same magnet, same hardware, same software for doing quantum computing. The question can be, why NMR? A major requirement of quantum computer is that the coherence should last long. Nuclear spins in liquid retain coherences for several hundreds of milliseconds, and the longitudinal state for several seconds. A system of n coupled spins, each spin half forms an n qubit quantum computer. A unity transform can be applied using RF pulses and coupling evolution. And various logical operations and quantum algorithms can be implemented. There is a problem though. In NMR samples has about 10 by 18 spins. Do we have 10 by 18 qubits? Unfortunately, no, because all the spins cannot be individually addressed. So far, the progress that we people have been able to do is to address spins which have different Raman frequency. So we then address them in different Raman frequencies. Each Raman frequency again contains 10 to the power 18 spins. So we get a result of a ensemble. So NMR is ensemble computing, it's not individual particle computing. And so we have to look for the result in terms of an ensemble. Okay. And one needs unequal couplings between spins yielding resolved transitions in a multiplet in order to encode information as qubit. I'll show you what that sentence means. For example of a heteronuclear 3-qubit system, which has been very popularly used by many people, is this. It's a dibromofluoromethane in which carbon 13 is enriched, and the bromines fall out because they have a spin 3 by 2, and they relax very fast within the bromine spin, and they get decoupled from the rest of the system. So we are left with 3 spins: fluorine, carbon 13, and proton. And they have a very large coupling, 200 hertz, 300 hertz, 50 hertz. And the advantage of large coupling is that the gate time is inverse to the coupling. The larger the coupling, smaller the gate time, or smaller the coupling, larger the gate time. And of course, we would like to have as small gate time as possible because we have to apply a lot of gates within one single coherence. Okay, so this is a very favorable molecule that many people have used, especially in our group. Okay, that's homonuclear spins, protons also form multi-qubit systems. For example, if you take a chloroform without enriching carbon, then it's single spin, which is what we are looking at, and it's a 1-qubit system. Okay, and it has one line. 1-qubit system, one line. These two protons have a slightly different resonance frequency because their environment, chemical environment differs, and therefore they resonate at a frequency difference of about 100 hertz, and the spectrum is given by this here. So this is four energy levels: 0, 0, 0, 1, 1, 0, and 1, 1. And this is first spin transition, this is first spin transition, and this is second spin transition, this is second spin transition, and the spectrum is this. This has a chemical shift about 100 hertz, a coupling of about 5 hertz, and a line width of 0.5 hertz. And we need the high homogeneity magnet to be able to do a control knot gate on this system. Okay, I'll show you how we do the control knot, but we need to resolve these two lines to do a control knot operation. Otherwise, we'll hit both the lines, and then we can do only a knot and not a control knot. We take a 3-qubit system, then we have it means all these 3 protons have different resonance frequencies, differ by about hundreds of hertz, and couplings are in tens of hertz, and line width is half a hertz, and this is a very good 3-qubit system. We have used it many times. Okay, we have to use a density metric description because this is an ensemble that we are looking at, and so we have to look for a pure state. Unfortunately, we don't have a pure state here. A pure state has the characteristic that trace rho is equal to trace rho square is equal to 1. For a diagonal density matrix, this condition requires that all energy levels except one have 0 population. Such a state is difficult to create in NMR. In optics, it is easy to do, but in NMR, the energy gap is too small. We will need uh, pico, pico Kelvin temperature to create such a situation. So, but what is done is David Corey found an way out, excuse, let us say, called said, let's not worry about pure states. We will do pseudo pure states. So what he did was he expanded the density matrix under high temperature approximation, and kept only the first term, because second term is of course very small. Here alpha is of the order of 10 to the power 5, and if you apply any unitary transform on the rho, it go this is this is this doesn't do anything to the unity, and it only affects on the delta rho. So delta rho mimics a pure state. We create a state in which all levels except one have equal population. Okay, such a state mimics a pure state. David Corey said this in 1997 or so. Okay, what's a pseudo pure state now? In a 2-qubit system, homonuclear and high temperature and high field approximation, the rho is given by 10 to the power 5 plus delta rho. So it has a Boltzmann distribution of population, which is 2, 1, 1, 0. But remember, it's not just 2, it is riding with a million. 10 to the power 5 is common. 10 to the power 5 plus 2, 10 to the 5 plus 1, 10 to the 5 plus 1, and 10 to the power 5. So we just take the 10 to the power 5 outside, and we look at the residual populations, and they form this the Boltzmann distribution. Okay, and so looking at this, a pseudo pure state is one in which all the states except one have zero population or equal population. Let us say, not zero, equal, because the 10 to the power 5 is riding everywhere. So this, so but then looking at just the delta rho, it looks like a pure state. Okay, that we have only population one level and not others. Now, so from equilibrium population distribution, we then go over to a pseudo pure state population distribution and carry out our NMR quantum computing. There are many methods for preparation of pseudo pure states that have been developed. The most important one of them is the spatial averaging method given by Corey himself, and there are logical labeling method given by Gershenfeld. We were the first one to experimentally verify the method. Temporal averaging by Kneel, and pair of pseudo pure state by Fung. Spatially average logical labeling technique by Mahesh, and long-lived single states by student S.S. Roy. I will not talk about all of them. I'll just talk about one or two. Spatial averaging. So this is the most commonly used method. So we prepare a equilibrium state, which is I1z plus I2z, proportional to, and apply a series of pulses with gradients to kill the XY magnetization in between. If we go through the algebra of this whole thing, we will end up with I1z plus I2z plus 2 I1z I2z, which is when you plug in the numbers is equal to 3 minus 1 minus 1 minus 1. You add 1 to it, it is 0 0 0 4. So that's the pseudo pure state. Okay. The logical labeling technique was championed by Gershenfeld. He, in a paper in Science in 1997, we had not started our quantum computing work till that time. We started in 1999. Okay, and one of the applications was to show that Gershenfeld's idea. What is the Gershenfeld idea? So we take a three spin system or 3-qubit system and look at the Boltzmann distribution: 4, 3, 2, 1. Okay, and 0, 0, 0 and 1, 1, 1. These are the states. This is the equilibrium state. Now we apply 2 pi pulses, interchange the population of this level and this level. Selective, very selectively we have to do this. And then we get a population distribution. You can verify that it is 2, 2, 2, 2, 4 and 1, 3, 3, 3, 3. And you will immediately recognize that these are subsystem pseudo pure states. this subsystem is a pseudo-pure state, and this subsystem is another pseudo-pure state. Okay, so this way we demonstrated this is the spectrum corresponding to this population distribution. You can sit down and think about it, and you will come up with this spectrum. Uh, this this was the first paper that we published in Physical Review in 2000, and we got started actually by a swap gate, but swap gate is coming up next. Over temporal, we are talking about still pseudo-pure state. So temporal averaging. See this Krill Chong in 1998 used this method to produce pseudo-pure state, and he was quoted by CNN at that time. Okay, so he did a very interesting thing. He says, "I'll do 3 experiments with 3 initial states of population. One in the equilibrium population. Of course, you recall that each one of them you have to add 10 to the power 5. Okay, and it's the deviation population here. And this, by interchanging these 2 populations, okay, and doing all the remaining algorithm and interchanging these 2 populations and doing all the other algorithm, and so long as all those operations are linear, we can add them. And so if you add these 3, it looks like as if we started with 6, 2, 2, 2. It's a pseudo-pure state. Let's look at quantum gates by NMR. Okay, there are 2 methods of doing gate operation. One is the coupling evolution. Okay, and I will do a control knot on this 2-spin system. But let me show you a control knot if you use the transition selective pulses. If I have an MR spectrometer, I can very precisely invert one transition without reflecting all other transitions. Then apply a pi pulse on this transition. Then you see I have done a control knot operation. Here was 1 and there was 0, and these are interchanged. So control on the first qubit, result on the second qubit. And the truth table of control knot is that only these 2 are affected, other 2 don't, nothing happens to them. But if you do using J evolution, you have to go through a little algebra. We started with a I1z plus I2z. 90-degree Y pulse converts it I1z to I2x. Apply a J evolution 1 by 4j plus 1 by 4j. This removes the chemical shift evolution. Okay, and this pulse, this plus together remove the chemical shift evolution and retain the J coupling evolution. And so that one needs to do some algebra to go from I2x to I1z, I2y. And you apply 90-degree x pulse here to second spin, and you get I1z plus 2I7z, I2z. And that is again a control knot operation. A knot operation is very easy, just a pi pulse on one spin. Okay. Actually, this is the swap gate, is the one which launched us into quantum computing. What had happened is Kavita was my senior student, and we were looking for new ideas to work with. And I suggested to her that you read a chapter on transition selective pulses in An's book. She read it and found out that if you apply a series of transition selective pulses, which is non-commuting pulses, you can interchange, you can work on subsystem, on zero quantum coherences, double quantum coherences, triple quantum coherences selectively. So this is the zero quantum subspace in which she worked on, and she showed that if you apply a pi pulse on this, on first transition, pi pulse on second transition, and pi pulse on this transition, a pi pulse on this transition, back a pi pulse on this transition, it interchanges the population of these 2 levels. Okay, actually, this if you apply alpha degree pulse here, it's an alpha degree rotation in the zero quantum subspace. Sorry, this is a lot of jargon here, but this is the best I can do. Okay, and so, but if you replace this alpha degree pulse by a pi pulse, it's a pi pi pi, and it interchanges the population of these two. We published this paper saying that we can manipulate the spins in the zero quantum subspace, the double quantum subspace, etc., etc. And lo and behold, Corey published a paper a few or earlier, that's or few weeks, months later, saying that this is a swap gate, and he did it using these pulses. Okay, and so we say, oh, you can do swap gate like this. We can do swap gate like this, and this launched us. We were not doing any quantum computing by NMR. We were still hesitating to start, and this is the idea and the experiment. Actually, he published a spectrum which is identical to the spectrum that we had earlier, and on same molecule by chance. And so uh, uh, we started our work on quantum computing by NMR, starting with this swap gate. A Toffoli gate is a control NOT gate. You require a lot of pulses, qubit selective pulses to do a Toffoli gate. But for a transition selective pulse, you need a single transition selective pulse to change the control on two spins, control NOT gate. So this out of the whole mess, only this has to be inverted, and that gives you a control NOT gate. Okay, these are just simple gates. A NOT gate is just inverse, not one gate. Not full NOT gate is just inversion of everything. Not one gate is inverting one spin. Control NOT gate is inverting this transition. Control NOT gate is inverting this transition, and this is logical gate using 1D NMR. Swap gate. Oh, I already showed you, but here it is swap gate. Pi pulse here. So interchanges. So it's a P1, P2, P3, P4. I interchange P3, P1. Then I interchange P3, P2. That's P3 has come here. And then back this. See, I end up with this population distribution, which says I have interchanged this population. This is pi pulse on 0, 1, and 1, 0. This is a swap gate. The truth table from the swap gate is 1, 1 is 1, 1, 0, 0 is 0, 0, 1, 1, 0 is 0, 1, and 0, 1 equals 1, 0. So, swap gate. Okay, the reason for this is the spectrum I was talking about with David Corey. The problem was I used a homonuclear spins, and if I interchange the population of these two levels, these two levels have equal populations. If I interchange the population, nothing will happen. I get a spectrum after a lot of hard work, which is same as normal NMR spectrum. And so, how to demonstrate that we have done something special? We then first did a control NOT operation, and then a swap, and then showed that this works. Okay, and after that we just started off doing many experiments. This is the Toffoli gate, in which you invert one transition, the 0, 1, 1, control NOT is this one, and just single transition you invert, and if you look at the population distribution, you will get this modified spectrum. Logic gates by 2D NMR. Well, Richard Ernst, although he was hesitant to work on quantum computing by NMR, he did publish one paper in which his 2D NMR, he had told about a preparation period, evolution period, mixing period, detection period. He had defined these people, and lot of 2D NMR work, Nobel laureate winning 2D NMR work was done using these preparation, evolution, mixing, and detection periods. He published this paper in Journal of Chemical Physics, and in which he renamed these periods as creation of initial state, labeling of the initial state, computation, and reading the output state. Using this idea, we use this same three-spin system. We looked at this first spin, zero spin, and we labeled the states of the other two spins on these transitions. So this transition has other two spins in 0, 0 state. This transition has other two spins in 0, 1 state, and this transition has 1, 0 state and 1, 1 state. So these are all this first spin spectrum, but the transitions are labeled according to the states of the other two spins. Okay. So then you actually, according to our protocol, you read this in the beginning and read the same thing again in the end. In between, you do some computation. And so this here, you see that we get beautiful two-dimensional gates. I had to add something to this picture. I did not, the Mahesh was a student who was just getting started when Kavita Durai was trying to finish up things. And one day Mahesh just came to my desk and put this piece of paper in front of me and said, this is a complete set of 2-qubit 2D gates. And we were all stunned. He didn't tell me how he did it. He himself found out what to do and how to do it and did it. In fact, Arvind, who was a theoretician, he had only one question. He said, how do you claim it's a complete set? He said, 4 into 3 into 2 is 24. I have the 24 gates here. And Arvind said, I'm convinced. So look at this. No, the first is no operation gate, not one gate. Look at the swap gate. That's beautiful. 1, 1 remains 1, 1. 1, 0 goes to 0, 1. 0, 1 goes to 1, 0. And 0, 0 is 0. The swap gate. And so this is very nice representation of the various gates using two-dimensional NMR. 3-qubit 2D gates, you need, of course, 1 extra qubit for reading. And the extra qubit for reading, in this case, is this one. Okay. And the other, no operation gate, nothing happens. Not one gate, flip the first spin to fully gate, control not gate, and or nor gate. And so this we published in Journal of Magnetic Resonance rather than Physical Review A. Okay, up till now, things that I have described to you, gates, etc., we have not utilized coherent superposition. We have, so quantum algorithms which utilize coherent superposition, I will show you 2 of them, DJ and Grover's Deutsch Joshua. These are proper names of the people, but it's abbreviated DJ gates. And Grover's DJ. If you have 1 qubit DJ, there are 2 variables. X can have 2 values, 0 and 1. In constant function, the function value remains same whether you flip this or this. And the balance function, half the time it takes one function value and half the time it takes another value. And Cleve gave a version which is given by this. And then you can look at 2 qubit DJ and the U that you have to do to verify the DJ is 1, not 2, control not 1, 2, control not 1, 2 bar. Okay, this I leave an exercise for people to understand how to do this. This is experiment. Apply a pi pulse, pi by 2 pulse, put them in coherent superposition. A pi by 2 pulse, put them in coherent superposition. And then apply a UF. The UF that I just mentioned, the UF is just this one. Okay, and then you have 1 qubit DJ, 2 balance functions, 2 constant functions, 2 qubit DJ, 2 constant functions and 6 balanced functions. Okay, you better accept it because published in physical review. All right, this is more interesting. Grover search algorithm. I pictorially show you how we do the Grover search algorithm. Actually, in algebra, it's a little more complicated. But this is you can go per state, of course, and then apply a coefficient with equal solution. It's called then you apply a you ask somebody. Of course, you have to know what state you're searching. So you take a black box, or you ask a friend of yours to come and invert the search state. Okay, and you close your eyes. You don't know which state has been searched, inverted. But then what you do is you invert inverted, and then do a inversion about the average values. And if you repeat this root n times, the desired state comes out with high probability. And this is Gover's search algorithm. Okay. And here is a demonstration of using 1D NMR. I actually don't like very much because there are too many things to be explained here. But let me just skip this transparency. It is Grover search algorithm using 1D NMR, but Grover search algorithm using 2D NMR is better. All the pulse sequences are hidden, UX and U00 are hidden, but you see the result. The input state given here, the search state is here. In this case, we start with same input state, which is 00, and search state in this case is 00. In this case, it's 01. In this case, is 10, and this case is 11. So this is a very beautiful demonstration of Grover search algorithm in a pictorial way. That you start with a 00, and your search state changes, which is either 00, 01, 10, or 11, and the 2D NMR gives you the pictorial answer for your search. This experiment was done by Ranbir Das. He did a lot of experiments in my lab, and then went over to US for his postdoc, and he converted himself to a protein biologist, and he's now working in CBS as a full-fledged biologist. So, achievements of NMR QIP. There are many achievements, and I don't want to spend time on this slide. Our own contributions are distributed to PhD and nearly 40 publications. I will briefly highlight some of these contributions. One is non-restricted discrimination of Bell states. Okay, this was given out by Professor Panigrahi, and he gave a theoretical approach as how to distinguish. And my student Jharna, who is no more, did the experimental non-restricted discrimination of Bell states. So these are the 4 Bell states: 00 plus 11, 00 minus 11, 01 plus 10, and 01 minus 10. These are the maximally entangled 2-qubit states, and Bell states play very dominant role in quantum computing. And so it's good to remember and learn what are Bell states, how to manipulate them, and these are entangled states. They cannot be written down as a single particle states. Okay, so this is very important. Yeah, I've written this here. Bell states play an important role in teleportation protocols. Oh, so Panigrahi actually is now published. At that time, it was in Conphys. Theoretical paper requires non-restrictive discrimination of the Bell states. And Jannarani did the experiment, of course, along with the discussion with Professor Panigrahi. Janna, in her 5th year, um, disappeared from this universe, and this paper is dedicated to the memory of Jannarani Samra. Professor Panigrahi had given taken two extra qubits to distinguish the Bell states. Okay, and so you need four qubit system. We had only 3 qubit system. So Janna did a very intelligent thing. She did. I will do a phase measurement in one, and another parity measurement in another. I'll re-prepare the Bell state and show that what to do, how it comes out. So if you do this, take the Bell state and put the ancilla qubit in Hazamat, position the control node operations, control node Hazamat, then you get Bell state here, and the Bell state is not destroyed, but you get the information. So first measurement gives you, if it gives you 0, and second measurement gives you 0, then this Bell state. If it's 1 and 0, it's got this Bell state. If it's 0 and 1, it's this Bell state. It's 1 and 1, it's this Bell state. Okay, go back. Then she took a three system, well-known 3-spin system that I showed you earlier, except that we have done the tomography of the density matrix, and this is the representation of the 0, 1, 0 pseudo-pure state, which says there is excess population only in one level, and all other levels have equal population or 0 population. Okay, excess population only one. So this is the pulse sequence for preparation of the PPS. All right. And pulse sequence is discrimination of the Bell state, is first preparation of the pseudo-pure state, then preparation of Bell states, encoding phase and parity information, and this for parity measurement oh, I can move this. Oh, I put it away. For parity measurement, the Hazmat gates are removed and control node gates are reversed. Okay, you just have to believe me. Oh no, it doesn't work. What happened?
So just click on the slide, sir.
Huh?
Click on the slide, sir, then click on.
It's stuck.
Or you can click on hide buttons.
Hide button.
Yeah, just beside the stop sharing, there is hide written.
A hide button. Okay. All right. Ah, yes. Works. Thank you very much. Okay. Yeah. Here's the result. Here's the pseudo-pure state. Pseudo-pure state can be represented by this spectrum also, or by tomography. Tomography was very beautiful. I liked the tomography, but you had to do a lot of experiments to get the tomograph. And here we read this spectrum is one needs only 3 spectra: proton, fluorine, carbon 13, and you get 1 line each. And this is pseudo-pure state. Tomography requires a lot of work, but these tomography have been done, and these are the created Bell states. Okay, so 0, 0 plus 1, 1. You can see there's a diagonal element 0, 0, 0, 0 and 1, 1, 1, 1, and now diagonal element 0, 0 and 1, 1. Okay, so this is psi plus, and this is psi minus because this goes back down, and this is phi, which is this one, and phi minus. So this is the prepared, created Bell state showed with the tomography. To show this with tomography, there's a lot of work to be done. And so we just stick to single spectra and population spectra after discrimination. And these two shows that it is psi plus, this inversion, and this shows psi minus, and this shows psi phi plus and phi minus. And so this is the non-discrimination of the Bell states. He was with us. He impressed upon us that we can experimentally verify his no-hiding theorem. And Jharna took up the challenge. And another student who is now professor at Berkeley, he gave up the operator U that I will tell you later. So the Brownstein and Pati had published a paper in Physical U Letters in 2007. Actually, Professor Pati, in his inaugural lecture, already mentioned about this no-hiding theorem and our experimental verification. Any physical process that bleach out the original information is called hiding. If you start with a pure state, this bleaching process will has the one unity. However, in a large space, it's unitary. I think this whole sentence, to make a complete sense. If you locally look, it's gone. But if you look at globally, it is there. Okay. That's my simple words. The no-hiding theorem demonstrates that the initial pure state after chemical unit reaction is completely transformed to this is a diagram Brownstein had given in 2007. It took a create a Bell state to two antennas. This is the theoretic, and on the Hadamard gates a U operation, control order operation, Hadamard gate and control order operation, and you see here gates, and here this initial state the only options, no operation side. Okay, but here you have to do operation this side. After randomization, the state size transferred to second angular qubit. No hiding theorem. Okay, conversion of the U matrix into a NMR pulse sequence has been achieved by a novel algorithmic technique developed in our lab by Ashoka Joy. This paper in 12 graphs of complete set of basis operators and develops an algorithmic technique for efficient decomposition given unitary into basic operators and equivalent sequence. The equivalent pulse sequence for the U matrix gave us the effect of doing more fluoromethane with carbon 13 enriched, I think so. Yeah, you apply some pulses and unity operations to all these spins, and you read out the state. Each U is described by this subset, and so it's a lot of work. Let me put it this way. Only Jharna had the patience to do this. And here is the demonstration. It is a very beautiful demonstration, and that's why you could publish it in Physical Review Letters. Actually, I was just writing something about Professor Ernst, and I published a paper in Physical Review Letters with him on what was that? In 1975 or so, and it took me 36 years to publish my second Physical Review Letters paper. So here is the initial state. These are each point on this surface is a initial state in the block sphere. Okay, You create these points on the blockosphere by applying a set of pulses 3 and then changing the theta and phi in steps of 15 degrees. So you get each point here is a pure pseudo-pure state in the blocosphere. Okay, but 325 such points were created. Okay, and there was nothing, no signal in the fluorine and the carbon. And then you run this experiment, and you get this result that nothing on the proton and nothing on the fluorine, and Ensela has the state psi is completely transformed from the first qubit to the third qubit. And this is an experimental demonstration of a theoretical assertion of Arunpati and Bramstein. A very beautiful experimental demonstration, and I'm very proud of this work by Jhata and Ashoka Joy. I'm nearly coming to an end, but I just want to say, already many people have talked about it, the quantum revolution that is going on right now. Sorry, aimed at 2016, released a 5 qubit and 10 qubit superconducting based quantum computer and placed it on the cloud for use of one and all, free of cost. My my last graduate student graduated in 2014, and then I started 14, and I started taking summer students. And my 2017 summer students did these 3 experiments using the IBM superconducting based quantum computer. I think it's called, so it has a name. Okay. All right, let me just show you what the hardware of the IBM computer. This, I'm sorry, this is the 2016 version. Okay. Arun Pati told something, what is the latest state in this, and they added some new coupling. The protocol using this, and you click it here and here. Oh, sorry. And so you run the computer in IBM lab, and they put access to you through the cloud. In the beginning, there were not too many users, so they were very freely giving it. I don't know what the status is. 10 qubit, they're restricted, and I don't know the status now. Please ask somebody who's a lot of people. One person in Panigrai's lab has published something like 100 papers using the IBM quantum computer. This is Bell state preparation, and so the protocol is you Hadamard and control knot, okay, and then measurement, okay, and you repeat this number of shots is 100. The probability is quite good, 0.5, 0.49, error in the third digit, and if you increase the number of shots, the error reduces, okay. Okay, non-destructive discrete Bell states using phase and parity checking circuits. This experiment was implemented on IBM computer by Anirban Pathak and his students, and my summer students repeated this, and they claim that they got a slightly higher fidelity, but I don't know whether it was just a simulation or it was an experiment. Okay. Also, the no-hiding theorem was demonstrated, and there are a lot of pulses we added, and then you get this result. Okay, thanks to IBM for developing such a wonderful experimental setup and making it available to one and all. There is this statement is 2-3 years old, but it's still valid. There is a great excitement in the quantum computing field. The pessimism of yesteryears, in which people were wondering that will a quantum computer be built in our lifetime? I mean, my lifetime. Of course, in your lifetime, it will be definitely built. Has been replaced by the optimism that a quantum computer will be built in the next few years, which will beat the fastest classical computer. I think this has already happened. Summary: NMR is continuing to provide a test bed for many quantum phenomena and quantum algorithms. Parliament has lots of students working with it. Their Professor Arvind was not my student. He was Mukunda's student, but Kavita Durai and Arvind are husband-wife, and they both graduated from IIT Kanpur, did the MSc from IIT Kanpur, and joined together here the same year to work with Mukunda and with me. Mahesh joined a few years later. They are both in either Mali. Arvind has recently become a director of another institute, I don't remember the name, near Sinha in CBMR Lucknow. Murli was working in IBM, and then he opened his own company here in Bangalore. And he did a very interesting experiment on I'm forgetting the name. Ranveer Das, I already talked to you about it. Rangeet Bhattacharya is neither Calcutta. Rangan Ghosh is neither Bhuneshwar, Avik Mitra, and Phillips. And Gopinath is in University of Minnesota. The last two students, Kritish Rao joined Bennett University in Noida. Manu is still in Minnesota. He's finished postdoc, but he's still hanging around there. Sapur Patel is a theoretician, our conscious keeper. Unless he approves, we don't send a paper to publication. And Professor Ramanathan, Professor Surya Prakash are the NMR experts, which basically they take all the, as our students take all the help from these people. And I sit in my room and just talk. The collaborators have been, of course, Malcolm Levitt from UK has been a very good friend and gave a very wonderful idea of liberated us from inbox thinking to output box thinking, and he said you any states that we have, you are free to rename them any way you like. There's no logical way of labeling it. It was a fantastic idea. So Parigrahi, Anupati, Aditi Sen, Ujjul Sen, I didn't show that work here. They came to visit us, and then we developed some experiment. Shoko Joy was a MSc student, me and a wonderful students from British Pilani, Goa, did PhD MIT, postdoc at UC Berkeley, and is now a faculty member at UC Berkeley. And the lecture is dedicated to memory of Jhanna Rani Samar. Thanks to NMR Center for spectrometer time, funding, DST, DAE, DBT, and thank you very much.
Thank you, sir. Your video is not visible, sir.
Eh?
Your video is not visible.
Video?
Yeah,
You couldn't hear me?
no, that's true. Your video is not visible right now on the screen.
Huh.
So maybe your low bandwidth is there. It is showing that low bandwidth. Okay.
I'm sorry, I don't understand what to say. What should I do?
Nothing, sir. Actually, your internet speed is low there. Maybe.
Oh, maybe because my internet
Yeah.
internet box is in another room.
Okay. That's why. Anyway, so
If I
any
was working, if I was showing it with my laptop, I would have gone to that room and shown. But
okay. No
but
problem.
my laptop is much slower than the desktop.
No problem. No. So it's I think any a question from audience or participants, because it's very nice lecture, which is truly given by Professor Anil Kumar ji. That is quantum information processing by nuclear magnetic resonance. Really, the experimental work which the group is doing, Professor Anil Kumar, is really very commendable and very remarkable. Just I have seen first time this experiment, because we are also theoretical worker. So any question from this participants, any want to question, any doubts, you can ask. Yes, any question from here? Okay. No question is there. So thank you very much, sir, for your this very understandable and very knowledgeable lecture. Yeah.
Okay. Have you
Really, sir. Really, sir. Sorry, sir. Sir, is I am audible?
recorded it?
Yeah, it is recorded because
Have you recorded
IISc has to send us. Yeah, it's recorded.
Yes, yes. Okay. Very good.
Your lecture is recorded. All lectures are recorded because of IICT instructions, and we have to air it on YouTube.
Please, I will send. Okay, good, nice. Please send me the YouTube link
Yeah.
later.
I will send you, sir. Huh?
Yes, I love to hear my own voice.
Yeah, sure. Thank you, sir. Thank you very much, sir. And if you
All
visit
right.
Gwalior, then you must visit to our institute campus.
No. That house has been sold. That house, this house was in Campo.
Okay.
It has been sold. Our parents, gone. Myself, I'm 80 years old. My wife is 76 now.
Okay.
But brothers live in one brother lives in Delhi, one in Calcutta, and there are a lot of sisters around. So we are big family.
But yeah, that's true, sir. But still, you are, sir, so dynamic right now. Because
Yeah.
my guide is Professor B.K. Agrawal from Allahabad. You know,
Oh yes, I know him.
Professor Balkrishna Agrawal.
Yes, I know him.
Yeah. So we also work like you. I am just reflecting the same gesture as you see in you also. He's also very devoted to research work, and we have learned a lot
Yes.
of things there. Okay, sir. Thank you very much, sir.
All right. Thank you very much.
Keep it. Thank you, sir.
Bye.
Thank you, sir. Okay. So you can leave it now.
I thought I left, but
Yeah.
apparently not.
Okay, sir. Okay, sir.
I will try to stop sharing.
Yeah.
Stop sharing. I think now it's gone.
Yeah. It's fine. So thank you very much, participants, and you must keep joining all those lectures, because it's very important and very understandable to know the new technology, the new concepts of quantum computing. Okay, so tomorrow we'll meet again, all participants. Thank you very much for today's lecture sessions. Once again, I thank you, everybody.
Thank you, sir.
Thank you.
How do I log out?
Thank you, sir. Thank you.
Yes, sir, end meeting, sir. That is from end meeting.
How
Thank
do
you,
I
sir.
log out?
Thank you.
Not allowing me to leave the meeting.